To understand what is special about these composed quantum systems, we have to introduce a more general notion of a quantum state, which is known as a density matrix. This describes a statistical ensemble of quantum states for a quantum system, including the possibilities that we might not know exactly which of these different quantum states our quantum system is in. So we start out with a collection of quantum states, psi indexed with an index I, and for each of these states we are going to assign a certain probability. So we have these pairs of states and given probabilities. And what we say is that each of these states may apply to our quantum system, but we do not know exactly which of the states it is. We only know the probability in which of these states our quantum system is in. What we are going to assume is that all the quantum states in this ensemble are normalized. And that also all the probabilities in here add up to 1. This has a very wide range of applications. For instance, we could have a set of quantum systems which are all of the same type. So we might have many copies of the same quantum system, just different physical realizations. Such as maybe atoms in a gas, and each of these atoms of course can be in a different state, and we do not quite know which of the different quantum states our atoms are in. And indeed this might be because we are talking about a system at a given temperature. So another setting in which this occurs is if you maybe have a complex system, all these atoms are of course actually interacting, so you maybe cannot even study them in isolation. But if they are interacting, then they could still define a certain temperature. So we encounter this in statistical mechanics. So this could apply, for instance, to a quantum system which is very complex, but can be described by a temperature. So you would assign probabilities according to the Boltzmann weights, depending on the energy of the states and the temperature. And this here is just the Boltzmann constant. A third setting could be that you carry out measurements, but you sort of forget to record the values of the measurements. Well, it could actually be that the measurement is just carried out by something in the environment that you just don't have access to. So you have the situation where your quantum system is going to be forced into one of the eigenstates according to the observation that is being carried out, but you have no way to find out which of the observable values this corresponds to. The only thing that you know are the different probabilities with which this occurs. So we can have the case where we do a measurement, but without knowing or recording the outcomes. So then these probabilities would just be obtained from the measurement postulate of quantum mechanics. And indeed, this can be viewed as a composed system, and looking at just a part of it, namely you have your quantum system that you're interested in, and the wider environment, say your measurement apparatus that is carrying out this sort of measurement, but you're not recording the value. So quite generally, and this is of course the case that we're interested in, this can be used to describe a part of a quantum system. Okay, so now let's have a look how we can achieve this. For this we are going to look at the averaged outcomes of our observations, A. And if we had a well-defined quantum state, then this would just be our expectation value, psi I, A psi I for the corresponding observable. But now, because we do not know which quantum state our system is in, we simply have to average this further using the probabilities that the system is indeed in this state. So this is a very natural generalization of these expectation values to the case that we do not quite know in which of the quantum states our quantum system is in. And now we can rewrite this in a very convenient form by introducing a formal trick, And we just need it in the derivation. At the end we will get a very useful and relatively simple result. What we are going to do is to introduce the identity operator at a suitable point, namely here. And as you recall, we can write the identity operator in any basis as this diagonal sum over basis states. So then we have here a sum over both indices, still these probabilities, and then here the first scalar product between the state psi I and n, and then the next scalar product between the state n and first the operator, and then the quantum state psi I. So this is just a formal stage of our calculation. Now we just have numbers at this point and numbers at this point, and we can just interchange the order of these numbers. So we still have this double sum, but I'm interchanging the order of the terms here in a very convenient way. Including putting this probability, which is also just a number, into the middle. And now we see that we can write this also in the following form. By just pulling these two sums apart. And using the power of the Dirac notation, we can even write it in a very suggestive form, namely like this. And then we can make two observations. First of all, we have this operation here carried out in a certain basis, but which basis we were using here was not important. It could have been any orthonormal basis. And what this does is to look at everything which is in the middle, which is a certain operator, and work out its so-called diagonal elements. So these are the matrix elements where the same index is applied for the row and the column, and we sum over all of them. Now this is a very standard operation on matrices and operators. It is indeed independent of the basis that we have chosen, because we have not specified this here at all, and this is known as the trace. So the trace of any operator, call it B, because here we have already a product involving A, is just defined in any basis as the sum of the diagonal matrix elements in this basis. And secondly, when we look at what we have here in the middle, then we have the operator A and a new operator, which we call the density matrix rho. So everything which is in here we call the density matrix rho. So this is an operator. It is not yet a matrix, but it will turn into a matrix very soon. Okay, so this is the so-called density matrix. Rho, and it's simply given as stated as the sum with these probabilities and the quantum states. So instead of working with these individual quantum states, we now have an operator that describes the whole collection of these states. So in other words, what we have derived for our statistical ensemble is the following identity, that we can calculate all expectation values by taking the trace of the product of the associated observable and this density matrix here, which is defined as I had given. Now this operator will look a little bit unfamiliar when you see it for the first time, but it has a range of really nice properties. So for instance, when all our quantum states are normalized, then we can re-express this by the following identity. And this can be seen in several ways. I will show it to you formally, and then I give you a very simple physical argument. So first of all, we can simply apply our definition. And insert here again the sum of all the different states. and then already take the scalar product from the other side, and just as before rearrange this. And carry out the sum over n here. But this is just going to give us the identity matrix. And now our quantum states are assumed to be normalized, and our probabilities have to add up to 1 as well, and therefore we will get our result. Now there is also a physical interpretation of this normalization, namely that this is just the expectation value of the identity operator. So this is just saying that the observable A is just the identity operator, so it just drops out here. Now the identity operator has eigenvalues which are all 1, so if you do observations you will just always get the same outcome, and if you average over this you have to get 1 as well. So this is indeed built into the definition that we started out with. And so it is not a surprise that in this bit more technical proof here, I just retraced our steps of the definition of the density matrix. The second key property is that this is a Hermitian operator. So ρ is equal to ρ dagger. And this is simply because when you take the Hermitian conjugate of any object such as this, you simply replace the states in the dual states. But in the definition of the density matrix, all the states appear just partnered with their dual state. And so under the Hermitian conjugation, this just does not change at all. So we have this property here. And this, of course, means that all the eigenvalues are real. Now I'm going to denote these eigenvalues as capital Pi and the corresponding eigenstates as phi I, so that we can write the density matrix also in the following form. And now one should probably wonder what this actually means, because this really just looks almost like the definition itself. However, in the definition, I mentioned that all the states that are involved in the ensemble are normalized, but I did not say that they need to be orthogonal to each other. Now what we can do, therefore, is to replace our original ensemble with probabilities little pi and possibly non-orthogonal states psi I by an ensemble of orthogonal states phi I with probabilities capital Pi. So you see that actually when we do observations on the quantum system, the ensemble is not necessarily well defined. We will have a choice. But this also tells us that there is an additional constraint on these eigenvalues Pi, because they are now probabilities, so they cannot be negative, and they can also not be larger than 1. And now, using this form, this we can of course also interpret as a basis. The trace of the density matrix, or this operator here, will just be the sum of the eigenvalues, and this has to be 1. So also again, these probabilities that we work out from these eigenvalues need to add up to 1, just as we had initially. These are all very useful features, in particular because they have these nice and clear physical interpretations, but this also has a mathematical notion, a technical term from mathematics, where you would call such an operator a so-called positive semi-definite operator. And this is really just saying that it has real eigenvalues and orthogonal eigenvectors, and none of the eigenvalues are negative. Now the key idea of the density matrix is that it generalizes the notion of a quantum state, so there should also be a limit where we just come back to the normal quantum states. And this is simply the case of a so-called pure ensemble, or we also call this a pure state. So this is an ensemble of states where we just have a single state with probability 1 and possibly many other states. but just with probability 0. So we can actually completely forget about them because they will not feature in our quantum system. And in this case, the density matrix simply takes the following form as given here. Now when we work out an expectation value in this case, this just takes the form as given here, and this just becomes by our proof, where we just retrace our steps backwards, just the normal expectation value. So this is the case in which we could just forget about the density matrix in itself and just can work with our normal quantum state. Now it would be nice if we had an easy way to figure out that this is the case. And this can be done by realizing that in this case ρ is a projection operator. I already mentioned these projection operators in the general postulates when we discussed how we can obtain the probabilities in the case that we have degenerate eigenvalues. And the key property of such a projection operator is that if you simply square it, it just becomes the operator itself. You can easily check this because if we apply this operator twice, just according to this definition here, then here we have our normalized quantum state, and so this just gives us the density matrix back. So this certainly works out, and this is certainly a nice way to check what is going on, but we can even condense this all into a number, into the so-called purity. This is also denoted by a p, and I realize that there are many p's in this course, so we will always have to make sure that we know what we are talking about. But this purity is defined as a trace of ρ squared. So first of all, we can see that for pure state, when trace ρ squared becomes just a trace of ρ, according to this rule here, we will just obtain 1 if we have a pure state. Now, in order to see what happens when we don't have a pure state, we are going to use the rule that we actually already applied here, namely when we take a trace of an operator, then we get the sum of its eigenvalues. Now, the eigenvalues of the square of an operator are just the squares of the eigenvalues. So we can write this also in terms of the eigenvalues as a sum over the squares. And now, because these are numbers between 0 and 1, this will in general always be less than the result that we obtain when we replace the squares by the numbers itself. But this was just 1, and the value 1 is only attained when exactly one of these values is 1 and all the others are 0. So in all other cases, when we don't have a pure state, this is a number which is less than 1. It is indeed then also positive, and it will be less than 1. And now we just need a name for this, and we call these states or situations a mixed state. So we have a very important distinction between two different types of statistical ensembles. Pure states, where we can work out quantum mechanics just in the way that we are familiar with a quantum state in a Hilbert space. And mixed states, which are more generalized situations where we do not quite know which of the quantum states our system is in. And these are indeed the two different situations indicated here. Now, I said the purity needs to be positive, and it can be at most 1. But what is the smallest value that it actually can take? It certainly cannot be just 0, because then all the probabilities would have to vanish, and this would not add up to 1. So let us assume that we have a quantum system with a Hilbert space dimension n. Then the smallest value that we can obtain is when all these probabilities here are 1 over n. And this we call the maximally mixed state. And now, when we work out what this means in terms of our density matrix, this simply means that the density matrix is 1 over n times the identity matrix, or operator in this case. And if we then work out the purity p, and I'm carefully writing that this p is indeed the purity because of those many p's, then we get the trace of 1 over n times the identity squared. So this becomes 1 over n squared times the identity operator, which has n eigenvalues which are all 1. So this just gives us 1 over n squared times n, so 1 over n. And this is indeed the smallest value of the purity that you can obtain in this quantum system. It could, of course, drop to 0 if you have a system with infinite dimensions, but in this course we are always interested in systems with finite dimensions. And so this is a very useful lower bound for the purity. So this corresponds to the situation where your quantum system might be in any state in your Hilbert space with the same probability. A little bit like going to the limit of an infinite temperature in a thermodynamic system. But this can simply occur for very simple systems when you just don't know enough about their quantum state. Okay, so we have these pure states, which are one extreme, and the maximally mixed states, which are another extreme, and in between you just have the normal mixed states, where you might have some idea of what the quantum states might be, but you're not completely certain. So we have introduced our more general notion of a quantum state. Nothing has changed in terms of our observables, and we've already worked out expectation values, so in terms of measurements nothing has changed as well. So the only thing which is left is the dynamics of the quantum system. So let's have a look at the dynamics of a quantum system described by such a density matrix. And what we mean by this is that we have a density matrix which now depends on time. And this is because the quantum states depend on time. So the probabilities in the definition of this ensemble do not depend on time. And then, just as in the Schrodinger equation, we would like to work out what happens when we change time incrementally. So we work out a derivative of this density matrix here. Now we apply this derivative to the states which we encounter here. But because we have two parts, we have to apply the product rule. So we have to calculate a derivative of this state or a derivative of this state here. So we get two terms. And in both terms we can use the Schrodinger equation. So the normal Schrodinger equation is written as IH bar ddt psi, and now for each of these states we're using the Schrodinger equation with the given Hamiltonian H. And we can formulate this also for the dual state. Where we use that the Hamiltonian is Hermitian, so we just obtain H also in the same equation. And now we can isolate these derivatives here, but just bringing the factors in front to the other side. And we can do this both at this place and this place here. And what we obtain in this way is the following expression, where this I is the imaginary unit and this is our summation index. And now we can take this sum, including these terms, to realize that this just involves again our definition of the density matrix. So we can simply rewrite this as the product of H and ρ, or ρ and H with the minus sign between the two different terms. And this of course just defines the commutator. So our final result can be written in the following form. And now this gives us the dynamics of this quantum system described by the density matrix. So this simply replaces the Schrodinger equation, And as before, the dynamics is simply generated by the Hamiltonian, which is the energy operator of this system. The system is still a well-defined quantum system with a given Hamiltonian. The only thing that we do not know is which quantum state the system is in. It would be quite interesting to maybe think also about systems where we don't know what Hamiltonian we have, but this is not what we are discussing at this point. This completes our discussion of the definition and the most important general properties of the density matrix. But now we should turn to a simple example, because in practice it is not as complicated as it might look from these abstract definitions.